So in the next talk, Qiushi will introduce how they enhanced the stealthiness and transferability of the adversarial attacks. Qiushi is currently a postdoc fellow in the Department of Computer Science and Technology at Tsinghua University. His research lies at privacy-preserving machine learning and confidential computation. So go ahead.
Thank you. Good afternoon, everyone. The topic of my presentation is enhanced stealthiness and transferability of adversarial attacks with class activation mapping ensemble attacks. Okay, my presentation mainly includes the following 5 aspects. As is well known, deep learning can be applied in the fields of finance, business, healthcare, and industrial, bringing them significant benefits such as enhancing the accuracy of data analysis, increasing production efficiency, optimizing resource utilization, and driving innovation and development. However, despite the positive impacts brought by deep learning, it also faces challenges in terms of security, such as adversarial attacks. Adversarial attacks can add a form of attack aimed at machine learning models, intending to deceive the model into producing incorrect output, the center's part. These attacks can be achieved by making tiny yet meaningful modifications to the input data, which are most ignorable to human observers. Adversarial attacks may result in the model producing wrong classification results, thereby impacting its performance and the reliability, especially in the critical domains such as the image classification, speech recognition, and facial recognition, and the autonomous driving. Consequently, adversarial attacks have become an important area of research in the field of deep learning. Understanding the principles and methods of adversarial attacks, exploring possible attack methods, and mitigating potential risks are essential to enhance the security and robustness of deep neural networks. Various adversarial attack methods have been proposed, including the optimization-based and gradient-based methods, which can achieve high success rates in the white box setting. However, in the black box setting, the attack efficiency is lower due to the inability to access the target model's internal details. Some transferability enhancing attack methods have been proposed to solve the above problem, including gradient optimization attack, input transformation attack, and model ensemble attack. However, these methods add perturbation to all pixel locations in the image, resulting in generated adversary examples with poor stealthiness and transferability. Okay, yeah. Several et al. Utilized machine learning interpretability tools such as the Shipley additive explanation to generate malware sample that would be misclassified as bind sample by a classifier. Inspired by its work, we attempt to employ the class activation mapping is a CAM to generate adversarial examples. We incorporate CAM score as weight for adding perturbations to each pixel, enhancing the attack capability for low attack epochs and stealthiness. Additionally, we improve the transferability of adversarial examples by ensembling CAM scores from multiple models. We will elaborate on our attack methods from two perspectives: target attack and non-target attack. The objective function for non-target attack is the left equation, and the first item is used to improve the attack capability of adversarial examples. Is the right line, the left right line part. The second term is used to improve their transferability among different models. Is the second red line part. We use the gradient variance optimization method and the score of the class active map to search the adversarial perturbation. And I think for the next part, the computation details of the class activation mapping score are as follows. Look like the left three equations. The objective function for the target attack is right corner, upper right corner. The optimization process for the target attack is consistent with that of non-target attacks. We validate our method mainly through 5 parts. It includes the perceptual evaluation, attack performance, and transferability, robustness, and evaluation studies. Due to the time constraint, robustness and evaluation studies will not be elaborated in detail. If you are interested in them, they can, I think we can be found on page 12 and page 13 of our paper. The dataset evaluation matrix baseline method and the target model involved in the validating the effectiveness of our method are shown in the table. And due to the time limit, we only visualize the adversarial example for 5 attack methods. If you are interested in the other examples, I think you should be, they can be found on the page 8 in our paper. And the figure shows the adversarial examples generated by our method and baseline method under non-target. The label represents the predicted label of ResNet 50. The result shows that our method generates adversarial examples with better perceptual quality than PGD, VMIFGSM, and MIFGSM under the same attack success rate. And the figure shows the adversarial example generated by our method and baseline method under target attack. In each module, our label represents the original label of the image. Tar label represents the target label. Epoch represents the iteration round of the target of the attack. ASR is the attack success rate against the target model. And the adv label represents the predicted label of ResNet 50. From the graph, it can be seen that only our method successfully misleads the target classifier to clarify as the specific label. The table represents the perceptibility of the adversarial examples generated by 10 attack methods with similar attack capability under non-target attacks. Specifically, when our attack capability is compared to the VMIFGSM and VNIFGSM, compared with VMIFGSM, our work drops by about 24% for L2, decreased by 13%, decreased by 13 for lower free, increased by 0.04 for SSRM, and increased by 0.69 for PSNR. The table demonstrates the demonstrates the result of the example generated by 9 attack methods with similar attack capability under target attack. This table shows that our method achieved the best efficiency among the 8 baseline methods with comparable attack capability, while the same NIFGSM performs the worst. The table displays the attack capability of our methods and the baseline methods in the non-target attack. Yeah. As the number of the attack epoch increase, the attack capability of 9 attack methods gradually strengthens until convergence. Compared to the baseline methods, our methods exhibits the fastest convergence and attack capability, significantly outperforming the baseline method at low attack epoch. The table shows the attack capability of our methods are baseline methods in target attacks. As the number of attack epoch increase, the attack capability of the 9 attack methods gradually increase until the convergence. Similar to the non-target attacks, our method shows the fastest and has the strongest attack capability, significantly outperforming the 8 baseline methods at low attack epochs. Starting from the 4th iteration, our attack capability supports VMIFGSM, and the strongest it is the strongest method by at least 10%. Particularly at the 10th iteration, our method's attack capability increased about 24% compared to VMIFGSM. From the table, it's also great. It can be seen that our method has a significantly better transferability than 9 baseline methods under non-target attack. Compared with the attack method VMIFGSM, our method improved the average attack ability against 13 target models by 11%. And compared with the most perceptible attack method, TPGD, improves the average attack ability by 13.7%. From the table, it can be seen that our method has a better transferability than 9 baseline methods under the target attack. Compared with the attack method VMIFGSM, our method improves the average attackability against 13 target models by about 23%. In conclusion, we solved 2 problems. We solved 2 problems: poor stealthiness and transferability. To solve above 2 problems, we first use class activation mapping method to discover the relationship between the decision of the deep neural network and the image region. Then we calculate the class activation score for each pixel and use it as the weight of perturbation to enhance the stealthiness of adversarial examples and improve attack performance under low attack rounds. In the optimization process, we also ensemble class activation maps of multiple models to ensure the transferability of adversarial attack algorithm. And about the results, it shows that our method generated adversarial example with high perceptibility, transferability, and attack performance under low round attack. Okay, so that's all for my presentation. Thank you very much.
Thanks, Qiushi. So you may notice that Qiushi is not one of the authors because the original author did not make it here because of the visa issue. So will you take the question from the audience or?
I can try to.
Okay, let's try.
Thank you. The only question I want to ask is that what is the rationale behind using separate substitute models for gradient and CEM computation? Thank you.
Okay, yeah. From my limited knowledge about this paper, I think the reason for the using substitute models for separate gradient and CEM computations is to enhance attack capability at low iterations and improve the transferability of the examples. So I think in the gradient computation, the substitute model is trained to maximize the loss function when attacking the target model. So I think which allows it to better reflect the gradient information and generate more effective perturbations. So I think I think is my own thought about this. Yeah.
Thank you.
Thank you very much.
Yeah. Okay. Anyone want another try? Okay, if not the case, feel free to contact the authors through email. And let's thank Qiushi again. So, please.